Autonomous robots improve delivery efficiency, reliability, and reduce costs by eliminating the need for human intervention.
In dense urban areas like university campuses, numerous ADRs are required to meet the ever-increasing demand, but their reliance on costly onboard sensors and computation limits scalability.
Our solution introduces a paradigm shift through an infrastructure-reliant model, removing the need for onboard sensors and reducing both manufacturing and maintenance costs.
This approach uses a mesh-based infrastructure that provides the ADR with extended sensory information, optimizing routes based on traffic flow and overcoming blind spots.
We aim to design, build, and evaluate an autonomous delivery system for food and other retail products, demonstrating the feasibility of coordinating ADRs through a distributed sensor network in dynamic and challenging environments, such as a university campus.
The robot is a basic system with a Raspberry Pi handling compute and receiving drive commands from a base station. It uses a differential drive controller to send velocity commands to the O-Drive motor driver with the ROS2 control framework, allowing for a modular hardware setup. Along a pathway, infrastructure nodes equipped with Z2I stereo cameras stream frames to the base station using GStreamer. The base station runs YOLO V8-based inference to detect key points on the robot. Stereo matching algorithms enable us to get 6D pose estimations, which are fused into a global position using an extended Kalman filter with the ROS2 robot localization package. For navigation, the ROS2 Nav2 framework with A-star path planning and dynamic window approach controllers used. The current setup relies on static map-based cost maps, and the controller outputs drive commands to the robot. We have a few plans to improve our current setup, and this involves dynamic mapping. It should be trivial to enhance the cost map with dynamic information from stereo camera depth images, generating point clouds for more accurate local control. The local cost map will roll with the robot using data from the nearby infrastructure nodes. And synthetic data generation. I'm currently implementing Isaac Sim Replicator to generate domain randomized datasets of 6D poses for NVIDIA Isaac ROS dope inference, replacing our method of manual keypoint labeling.
Behind the scenes of our ADR system lies a complex network of technologies that enable seamless connectivity and back-end computing. To start, we conducted research on various connectivity options, including Wi-Fi, CLF 4G and 5G, and LoRaWAN. We calculated theoretical numbers to determine the minimal requirements for latency, bandwidth, and range. Next, we explored different network topologies before settling on a partial mesh network, which proved ideal for a fleet of ground robots. This design allows for efficient communication between robots and ensures reliable data transfer at a lower cost. We first opted for a Wi-Fi based solution using ESP32 modules, but after some development it did not meet our performance expectations. We then settled on an off-the-shelf system from TP-Link, which outperforms our in-house solution. On the back end, we set up a Docker swarm of multiple servers, which allows us to scale and replicate compute and other processing services to ensure reliability and high availability, even in the event of component failure.
The foundation of the ADR is its chassis, divided into three key sections: the base, which houses the electronics, the outer walls providing structure, and the inner walls creating 4 separate compartments. These compartments can hold up to 4 orders simultaneously, designed to fit any size meal on campus, including family-sized pizzas. This allows the ADR to efficiently handle multiple orders. The top 3 compartments have roller-style lids that retract into the chassis, offering easy access to both the top and front. The bottom compartment uses a pivot door for quick sliding of items in and out. The 3D printed shell gives the ADR its distinct look and houses features like an LED strip for communication and time-of-flight sensors in the front and rear, ensuring collision prevention. The MCAV logo is featured throughout the design, including a front badge and patterns on the lids, reinforcing its identity as a cutting-edge delivery solution.
The ADR's drive and suspension system is designed for smooth, efficient navigation across varied, rough terrain, ensuring both stability and manoeuvrability. The robot features a differential drive system powered by two 350-watt hoverboard wheel hub motors. Each motor independently controls one of the two front drive wheels, allowing precise steering by adjusting the speed and direction of each wheel. This enables the ADR to perform zero radius turns, making it ideal for navigating narrow pathways and confined spaces without the need for complex steering mechanisms. The suspension system complements the drive with an adjustable double wishbone design for the front wheels and a 3-link panhard suspension for the rear caster wheels. This setup evenly distributes the load and maintains traction, allowing the ADR to traverse rough surfaces like stones and cracks. Placing the drive wheels at the front ensures that the robot can pull itself over these obstacles and the rear caster wheels are less likely to catch on uneven terrain. Together, these systems enable the ADR to navigate smoothly and efficiently, providing excellent manoeuvrability even in the tight or challenging environments.
Powering the ADR is a relatively simple but safe and reliable power system. Powering it all are 3 LiFePO4 battery packs put in series, which provide 36 volts with 8 amp hour capacity, which is enough to last over 4 hours under conservative assumptions. When designing the power system, we considered the impact of ground loops and ground noises. We addressed these with the use of USB isolators on sensitive electronics, grounding topology similar to star grounding, and a brake resistor for our brushless DC motor driver to protect it from power generated by the motor during deceleration. To make the ADR safe, we included safety features such as fuses, an isolator switch, relay power cutoff, and an emergency stop. These options should allow the ADR to stop reliably during unexpected events. We designed custom printed circuit boards using Alchem Designer. Some of the considerations we noted were clearance of high voltages, heat dissipation, and impedance control of sensitive high-speed signals. Our project began by addressing the need for scalable, cost-effective ADRs in densely populated environments.
Through the development of our infrastructure-reliant model, we've demonstrated the usefulness of an alternative to traditional heavy onboard sensor method.
By shifting almost all the sensory and computational burden onto the back-end and infrastructure, we were able to create a more scalable and cost-effective delivery system.
However, we believe that a more optimal balance between onboard sensors and infrastructure will enable further cost optimizations.
This should let us take advantage of the scalability of infrastructure and the reliability of onboard sensors.